My name is Vishesh Verma. I'm going to talk about the work we have done on estimating the slopes of organic field effect transistor transfer characteristic curves with an eye to mobility estimation. Organic field effect transistors, or OFETs, are becoming increasingly popular because of their versatility. They have found uses in such applications as artificial skin, RFID tags, flexible devices, and biological sensors. However, OFETs have relatively low mobilities. Much work has been done to increase their mobilities. The mobility is estimated using the slope of the transfer characteristic curve. The estimate is sensitive to changes in the measured value of the slope, so accurate estimation of the slope is crucial. Accuracy can be increased by combining estimates from multiple OFETs. Combining multiple estimates into one also enables us to gauge the uncertainty in the final estimate by computing a confidence interval, which we can't do if we have an estimate from just one OFET. I'm going to discuss slope estimation approaches that employ this strategy. I'm also going to discuss a web application that implements one of them. The app automates or simplifies the steps of mobility estimation and gives results that are less subjective and more reproducible. Let me begin by reviewing how the mobility is estimated for a single OFET. Each panel of this plot displays a transfer characteristic curve that relates the square root of the saturation drain current to the gate voltage for an N-type OFET. Mobility estimation typically consists of three steps. In step 1, we choose a range of gate voltages over which the curve is roughly linear. We shall call this range the regression range. In the left panel, it lies between the two vertical red lines. In the second step, we perform linear regression over the regression range. We can then compute a mobility estimate, mu hat, by taking the slope beta hat of the fitted line and plugging it into this formula. L, W, and CG represent the channel length, channel width, and gate capacitance, respectively. The regression range must be chosen with care. If the regression range is too wide, as in the left panel, then beta hat will be too small, or biased downward. If the regression range is too narrow, then beta hat will be based on a small number of points, so the uncertainty or variability in it will be high. Typically, there are multiple OFETs in an experiment. The OFETs may be grouped, and we may want to compute one mobility estimate for each group, as it would be more precise than any estimate for a single OFET. One strategy for doing this entails the following. First, we fix a regression range, as in the left panel of the plot. Second, we compute the slope for each OFET using that range, as in the right panel. Third, we estimate the mobility for each OFET using the formula shown earlier. Finally, we average the mobility estimates. An alternative strategy stems from viewing the slopes of the OFETs in the group as draws from a distribution with mean mu beta. In this alternative strategy, we first compute an estimate mu beta hat of mu beta. This may involve fixing a regression range as in the first strategy. We then compute a group-level mobility estimate by plugging mu beta hat into the formula from earlier. There is a problem with using a fixed regression range that is illustrated by this plot. In the left panel, the regression range is based on the blue curve and is too wide for the orange curve. In the right panel, the regression range is based on the orange curve and is too narrow for the blue curve. Thus, a fixed regression range could be too wide for some OFETs in the group and too narrow for others. We use simulations to evaluate 4 approaches to estimating mu beta, or step 1 of the alternative strategy. The first 3 use a fixed regression range. The naive approach assumes that OFETs have the same slopes and the same intercepts. The mixed model approach allows slopes and intercepts to vary and assumes that they're normally distributed. The two-step approach allows slopes and intercepts to vary, but doesn't make any assumptions about how they're distributed. The fourth approach, the nonlinear regression approach, is similar to the two-step approach, but doesn't require a fixed regression range. The fixed regression range approaches can be derived from this space model. Here, I represents the saturation drain current and V represents the gate voltage. The model assumes that for the kth OFET in a group of n OFETs, for each gate voltage in the regression range, the square root of the saturation drain current is a linear function of the gate voltage plus a random error epsilon. A subscript k is in the intercept and slope to indicate that they may vary across OFETs. We assume that the intercepts, slopes, and errors are random and represent their means and variances as shown. For example, we assume that the mean slope is mu beta. The naive approach uses the base model with the assumptions that the alpha k's are equal and that the beta k's are equal. The mixed model approach uses the base model with the assumption that the alpha k's and beta k's are normally distributed. The two-step approach uses the base model as is. Here's a more detailed description of the two-step approach. It fits one linear regression model for each OFET and then averages the slope estimates. In its first step, we choose a regression range. In the second step, for each OFET, we fit this linear regression model over the range. We then average the slope estimates from the fitted models to estimate mu beta and construct a confidence interval. The nonlinear regression approach differs from the other approaches. Without a regression range, it fits one nonlinear regression model for each OFET and then averages the slope estimates. In the first step, we fit this model for each OFET. In this plot, the solid curve is an OFET curve, and the dashed curve is the model fit to it. The model is piecewise linear. It has a flat piece whose y-intercept is gamma k, and a slanted piece whose intercept and slope are alpha k and beta k, respectively. We next estimate mu beta as the average of the slope estimates from the fitted models and construct a confidence interval. We performed simulations to evaluate the four approaches. Different simulations corresponded to different combinations of parameters. These were set to achieve certain signal-to-noise ratios, or SNRs. The SNR measures the messiness of a dataset. Each simulation consisted of 200 runs. On each run, a dataset was created using the simulation parameters, and each approach was applied to the dataset. This slide lists the simulation parameters and their values. The number of OFETs in a group ranged from 6 to 48. Several SNRs were used. 20 corresponds to high messiness and 200 to low messiness. The slopes of the linear parts of the OFETs were drawn from a normal distribution with mean mu beta and standard deviation sigma beta. Mu beta equaled 4, and sigma beta was between 0.25 and 1. The threshold voltages were drawn from a normal distribution with mean 0.5 and standard deviation 0.25. For the fixed regression range approaches, 3 ranges were tried: a wide range, a medium range, and a narrow range. This plot shows what a simulated OFET curve looks like. The curve is roughly flat up to the threshold voltage. Beyond the threshold voltage, it is roughly linear. Datasets for 12 different pairs of signal-to-noise ratio and sigma beta are displayed in this plot. Each panel shows one 12 OFET dataset, with one of the OFETs highlighted in black. Note that as sigma beta increases, the linear parts of the curves fan out, and as the SNR increases, the curves become smoother. The real experimental datasets we've seen resemble these 4 datasets more than the others. So, it's more important for an approach to perform well on datasets like these, datasets with a high SNR and a low sigma beta. We evaluated the approaches on 3 measures: coverage, confidence interval length, and bias. The coverage for an approach in a simulation is the proportion of the 200 runs where the 95% confidence interval produced by the approach contained mu beta. The coverage should be close to 0.95. This plot shows the coverage results for simulations where the group size was 6 OFETs and the regression range was narrow. The coverage is on the vertical axis. There's one column for each approach, with each approach name being abbreviated. To give an example of how to interpret the plot, this gray dot means that the naive approach coverage for the simulation where the SNR was 20 and sigma beta was 0.25 was around 0.97. Here, the coverages for the approaches were in the neighborhood of 0.95, but the naive approach coverages decreased as sigma beta increased, and the mixed model approach coverages tended to be a fair distance below 0.95. The nonlinear regression and two-step approaches didn't have these problems. The contrast between the approaches was starker for the wide regression range. All of the approaches did worse, particularly the naive and mixed model approaches. However, the nonlinear regression and two-step coverages were still close to the target. The confidence interval length for an approach on a run is the difference between the upper and lower endpoints of the confidence interval produced by the approach on the run. The length should be small, as the smaller it is, the more precise our estimation is. This plot shows the length results for the simulations where the group size was 6 OFETs and the regression range was narrow. For example, this box plot represents the distribution of the 200 naive approach lengths for the simulation where the SNR was 20 and sigma beta was 0.25. In several simulations, the naive and mixed model lengths tended to be smaller than the two-step and nonlinear regression lengths. However, as we just saw, the naive and mixed model coverages were frequently off-target. On-target coverage is more important than a small length. Note that in some simulations, the two-step lengths tended to be larger than the nonlinear regression lengths. A narrow regression range contains few measurements, so there's high uncertainty in the slope estimates produced by the two-step approach when the regression range is narrow. The nonlinear regression approach doesn't use a regression range and thus doesn't have this problem. The bias for an approach on a run is mu beta hat minus mu beta, the difference between the approach's estimate of mu beta on the run and the true value of mu beta. The bias should be close to 0. This plot shows the bias results for the simulations where the group size was 6 OFETs and the regression range was wide. For example, this box plot represents the distribution of the 200 naive approach biases for the simulation where the SNR was 20 and sigma beta was 0.25. In some simulations, the biases for the naive, mixed model, and two-step approaches tended to be negative. A wide regression range is liable to contain measurements with the gate voltage below the threshold voltage, so the slope estimates produced by the fixed regression range approaches tend to be too small or negatively biased when the regression range is wide. The nonlinear regression approach doesn't have this problem since it doesn't use a regression range. We can modify the four approaches so that they can be used for difference detection. If we want to determine whether two groups of OFETs have different values of the mobility mu, then we can test whether they have different values of mu beta. Difference detection could be useful in a situation where we want to gauge the impact of a choice made when constructing OFETs, like a choice of thickness for a layer. If we're considering two thicknesses, then we could build OFETs with each of them. We could use difference detection to check whether the mobilities for the two thickness groups are different. As an example of a modified approach, the modified naive approach applies the naive approach from earlier to each of the two groups, which produces a mu beta estimate for each. Next, a t-test is used to test the hypothesis that the mu beta values are equal. If the p-value is below 0.05, then the hypothesis is rejected and we conclude that a difference exists. We evaluated the modified versions of the four approaches in simulations similar to those described earlier. This plot shows what a simulated dataset looked like. Each dataset consisted of 5 groups of OFETs, one of them being a baseline group. The mean slopes for the other 4 groups differed from the mean slope of the baseline group by 0, 0.5, 0.75, and 1. For example, this panel shows the baseline group, which is colored red, and another group, which is colored blue and has a mean slope that is 0.5 higher than that of the baseline group. The dark curves show the trends for the two groups. We evaluated the modified versions of the 4 approaches on 2 measures, false positive rate and power. The false positive rate for an approach, in a simulation where the difference in mean slope is 0, is the proportion of runs on which the approach mistakenly detected a difference. The false positive rate should be around 0.05 since we reject the hypothesis of equal mean slopes if the p-value is below 0.05. This plot shows the false positive rate results for the simulations where the group size was 6 OFETs and the regression range was wide. The nonlinear regression and two-step rates were close to the target of 0.05, but the naive and mixed model rates were well above 0.05 in several simulations. The power for an approach in a simulation where the difference in mean slope is non-zero is the proportion of runs on which the approach correctly detected the difference. The power lies between 0 and 1 and should be close to 1. These are the power results for the simulations where the group size was 6 OFETs and the regression range was wide. The nonlinear regression and two-step approaches had similar power in many of the simulations. In some simulations, like those with a small value of sigma beta, the nonlinear regression approach had higher power. In several simulations, the naive and mixed model approaches had higher power than the nonlinear regression and two-step approaches. However, because they had off-target false positive rates, they're grayed out. The simulations show that the nonlinear regression approach is better than the other approaches. It's also better because it doesn't require the researcher to choose a regression range and thus eliminates a source of subjectivity. We have created a web application that implements the nonlinear regression approach with the goals of automating as much of the analysis as possible and making the results less subjective and more reproducible. It can be accessed at this link. The app takes as input a data file that must look like this. There must be one sheet for each OFET. On each sheet, there must be a gate voltage column and a drain current column. It's assumed that data for both the forward and backward sweeps are included. Here is the app. The Directions tab has directions for using the app and links to YouTube videos that show how to use it. The user must begin on the Main tab, where they need to upload a file and enter various pieces of information, like the names of the gate voltage and drain current columns, the number of OFETs, the channel lengths, and so on. On the Outlier Flagging tab, the user can flag OFETs as outliers if the data for them looks abnormal. OFETs can be flagged manually. The app can also suggest which OFETs to flag. The Model Fits tab shows the fit of the nonlinear regression model for each sweep of each OFET. It also displays some numerical measures of fit quality. The OFET Summary tab displays the user-entered information for each OFET, as well as estimates of the threshold voltage and the mobility. The Group Summary tab shows threshold voltage and mobility estimates for the various groups. The groups are defined based on the user's choices on the Main tab. Also shown are the measures of the uncertainty in the estimates. We can download the numbers calculated by the app by clicking this link on the Main tab. We get an Excel file that presents numbers at the sweep, OFET, and group levels. There are several possible directions for future work. One direction involves improving the fit of the nonlinear regression model for curves that it describes well. The solid curve in the left panel of this plot is such a curve. The dashed curve is the fitted model. The transition between flatness and linearity could be modeled better. The OFET curve has a bend, whereas the fitted model has a corner. The fit to the linear part is quite good, but it potentially could be made better by weighting the measurements during the fitting process. Another direction involves figuring out how to model curves with a kink, like the solid curve in the right panel. The fitted model fits poorly. Possibly a piecewise linear model with 3 pieces would fit better. One piece would go here, a second piece would go here, and a third would go here. A third direction involves adding additional useful features to the app. That concludes our presentation. Thank you for listening, and please reach out if you have any questions.